Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Arusi. In today's session, we will be looking at the qualitative analysis of ions. So we are continuing with our series on practical chemistry. And as usual, I will at various intervals be stopping to take any questions you've got. Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost. I do apologise for the feedback from my monitor. That has been dealt with. So I will be stopping at various points to tackle any questions you've got for me. And as is traditional now, towards the end of the session, we will look at a few practice questions looking at qualitative analysis of ions. So this is essentially an extension of work, or the sort of analytical work you'd have carried out at GCSE. There are new elements, of course, at A level. For instance, you are now required to be able to identify the halides as their solids using sulfuric acid, for instance, and exploring their redox chemistry as a means of identifying the different halides. So we will look at that towards the middle part of this session. And as usual, I will join the session using my tablet. So if you give me a few seconds to do that, we will be ready to roll. Excellent. So hopefully you should be able to see on your screens my title page, Qualitative Analysis of Ions. And we will start by looking at some familiar metal ions. So we'll start by looking at cations and in particular group 2 metals. So on your screen, we've got our first chemical test for group 2 metal ions. And like a lot of metal ions, some of the group 2 metals will form precipitates when reacted with sodium hydroxide. So this test relies on the ability of some of these group 2 metal ions to form the metal hydroxide precipitate. Of course, if the metal hydroxide is insoluble, it provides a means of identifying the metal ion present. Okay, so how is this test actually carried out? Well, you've got a very straightforward method on the screen, and this involves a small volume of your test solution containing your metal ions placed into a test tube, or perhaps a boiling tube. A test tube would be more appropriate. And as you can see there, it only requires a few drops, about 10 drops, and a fairly dilute solution of your metal ion. And to this, you're going to be adding a similar volume of sodium hydroxide, also reasonably dilute. We've got about 0.6 moles per decimeter cubed in this set of instructions here. So you're going to be adding 10 drops of your sodium hydroxide solution to the 10 drops of your metal ion solution. And for the group 2 metals, the metals at the top of the group, so we're looking at magnesium and calcium, will form insoluble metal precipitates of the hydroxide. Okay, so that is a good way of identifying magnesium hydroxide, also known as magnesia, and calcium hydroxide, which you will have come across and be more familiar with as lime water, which you would use in that characteristic test of carbon dioxide gas. Okay, so once you've added your drops of sodium hydroxide, you want to add it until your sodium hydroxide solution is in excess, and with gentle shaking to elicit the formation of your precipitate. Okay, so you've got magnesium hydroxide, which forms a white precipitate, and calcium hydroxide as well, which forms a white precipitate. And we can write an overall equation, or perhaps an ionic equation for both of these reactions. So in the case of magnesium ions, we've got Mg2 plus aqueous, say perhaps from magnesium chloride, and to that you're adding hydroxide ions, OH minus, and aqueous OH minus ions, and you are forming magnesium hydroxide, which is, of course, a precipitate, so it's going to be solid, and that means that we will need 2 moles of our hydroxide ions to form the precipitate. Okay, so that's your balanced ionic equation, and you would be able to write, or should be able to write, a similar equation for the formation of your calcium hydroxide precipitate. Now, as you can note here, not all of the group 2 metals form the metal hydroxide precipitate. The hydroxides of strontium and barium are rather soluble, and so you will not get a precipitate being formed. And that tells us a little bit about the trends in solubility of our group 2 hydroxides, as well as a little bit about the alkalinity of the hydroxides formed, which we will look at very shortly. So as far as the trends in solubility go, okay, so the solubility of your group 2 metal hydroxide increases down the group. Now, as far as the alkalinity goes, the more insoluble your metal hydroxide is, so in other words, magnesium and calcium hydroxide, the fewer hydroxide ions you're going to have in solution, and therefore the less alkaline your metal hydroxide is going to be. So the trend in alkalinity would be opposite to the trend in solubility. Okay, so the most alkaline group 2 hydroxides will be the most sort of soluble, so down at the bottom. So we're talking about strontium and barium, and as you go up, solubility of the hydroxide decreases, and so the alkalinity will also decrease. Okay, so that's the first test we've encountered, and probably one that you would have first seen in one form or another in your GCSE years, relying on the formation of a metal hydroxide. Okay, so let's look at the tests for positively identifying strontium and barium. Given that we know that they're not going to be forming hydroxide precipitates, can we react them with another reagent in order to get the precipitate of containing strontium or barium ions? And there is exactly such a reagent in the form of sulfuric acid. Okay, so we're looking at group 2 metal ions still. So we're looking at these cations, and we've just seen that at the very top, so magnesium and calcium will form metal hydroxides that are insoluble, but further down you will get soluble hydroxide, so no precipitates are formed. So in the case of barium and strontium, we want to form a sulfate precipitate. And how do we do that? By reacting your solution containing strontium or barium ions with sulfuric acid. Okay, so the method is again very straightforward. Again, note the small quantities of the solutions of the test solution and the reagent required. So again, 0.1 mole per decimeter cubed of your metal ion solution in a test tube, and to that you're going to be adding 1 mole per decimeter cubed sulfuric acid, and you're going to be adding about 10 drops, so an equal volume of your test reagent. And again, you're going to be adding your sulfuric acid dropwise with gentle shaking until in excess. And at that point, if your solution contains strontium or barium, you should be able to see a white precipitate of strontium sulfate or barium sulfate as shown in the observations box. Now, for the sulfate, sulfate compounds formed for the group 2 of the group 2 metals, the trend in solubility is the opposite for that of the hydroxides. In other words, the group 2 metals at the top form sulfates that are very soluble, and that solubility reduces or declines as you go down the group. Okay, so we can again write an ionic equation to illustrate the formation of our precipitate. So we've got strontium ions, Sr2 plus aqueous, being reacted with sulfate ions, SO4 2 minus aqueous. And as a result of this reaction, we're ending up forming strontium sulfate, which is solid. Okay, and you should be able to write a similar ionic equation for barium. And as we've just mentioned, the trend in solubility of the group 2 sulfates is the opposite of the group 2 hydroxide. So okay, so if you have a group of, or let's say you have 4 unlabeled bottles containing solutions of group 2 metal ions, these are 2 sort of tests you could use to separate them into at least 2 groups. So you would be separating them into one group that responds, or gives a positive result or precipitate when tested with hydroxide, and the other group which gives a positive or precipitate when tested with your sulfuric acid. So your metal hydroxide precipitates with the magnesium calcium hydroxide, and your metal sulfate precipitates with the strontium and barium sulfate. Okay, so 2 tests, or 2 different tests to allow us to identify group 2 metal ions. At this stage, I will pause briefly to check that there aren't any questions for me, and if not, we will continue with our work. So looking at the chat box, there is nothing in there as yet, so we will continue with our work. And what we want to do next is to look at perhaps the one atypical cation that you would come across, and this cation, of course, is ammonium. And with all the cations that you would be dealing with, they are almost always metal ions. Ammonium is a good example, a common example of a non-metallic cation. So it's of course, your ammonium molecule having acquired a proton becomes the ammonium ion. So how do we test for ammonium ions? So the test for ammonium ions relies on the same reagent as we've seen for testing for many metal ions. And again, this is sodium hydroxide. The sodium hydroxide is, of course, an alkali. The ammonium ion is acidic. It can donate a proton. And in doing so, you've got your H+ ion reacting with the hydroxide ion. Of course, you would form water. But that leaves us with ammonia gas being formed as well. And gentle warming of your test tube will liberate this ammonia gas, which you can test with red litmus paper, damp red litmus paper, which should turn blue when your ammonia gas dissolves in the water in your litmus paper. Okay, so let's look at how this is carried out in practice. So you only place, again, 10 drops. So in these qualitative tests, the key point to make is the small, the minimal volume of solutions of the ions and reagents that you need to give a positive test. So we're not talking about large volumes of solution here. So 10 drops of your ammonium chloride, which of course contains your ammonium ion, that's going to go in a test tube, and you're going to be adding about the same volume, so 10 drops of 0.4 mole per decimeter cube sodium hydroxide. It's a slightly more concentrated reagent than the test solution, and you're going to shake the mixture. Okay, so this allows your neutralization reaction to happen, and the ammonia that is formed, which is likely to remain in solution, will be liberated or released from the test tube by gently warming the mixture. Okay, so gentle warming in a water bath allows the ammonia fumes to leave your test tube, and these the fumes can be, or the ammonia gas can be detected by holding a damp red litmus paper over the mouth of your test tube, and that should turn blue. Okay, so red litmus paper is turned blue by the ammonia gas form, which of course is alkaline. So again, this is a test that you would first have encountered at GCSE, and it is still an important qualitative test for identifying ammonium ions. Okay, so that rounds up are tests of different metal ions at this stage. Now, there are obviously a large number of transition metal ions that you would also be required to test for at in your second year. And so all I'd like to say about that is that the tests for those transition metal ions follows a very similar pattern to what we've just seen here, in that you would invariably be adding a solution of sodium hydroxide to your solution containing your transition metal ions. The difference, of course, between the transition metal ions and the group 2 metal ions we've just seen is that the transition metal ions will form colored precipitates of various hydroxides. And also you can also look at other reagents for testing for transition metal ions. You can add dilute ammonia, which in many ways will behave just as with the hydroxide, because dilute ammonia in water obviously forms hydroxide ions. Where there is a difference is in, for instance, the use of concentrated ammonia or adding an excess of ammonia, at which point you begin to see ligand substitution reactions happening. Okay, so those are tests that you will be carrying out in your second year. Again, for the purposes of our PAG-4 qualitative analysis of ions in the first year, you will not be seeing transition metal ions being tested. Okay, so let's move on to tests for anions then. So we're moving on to negatively charged species, and the first one to look at is the sulfate ion. Okay, so we have seen from our work on the group 2 metal ions that you can form a sulfate precipitate with barium and with strontium, and so a good way of detecting sulfate ions in solution is by adding a test reagent containing barium to your test solution. Now, it is important, however, that you acidify your barium chloride in this case, because you don't want so if there are any carbonate impurities present in your test solution, addition of barium chloride would form barium carbonate, as well as any sulfate, as well as barium sulfate if there are any sulfate ions present. And if there are sulfate ions present, the formation of your barium carbonate would indicate a false positive result, because you would have the contaminant carbonate ions forming the precipitate of barium. And so it is very important that you acidify your barium chloride solution first, and that hydrochloric acid will react with any carbonate ions present to get rid of it, and you should be able to see fizzing if there are carbonate ions present, and that fizzing, of course, represents the formation of carbon dioxide gas. So in testing for sulfate ions, it is important to acidify your barium chloride, and it says if acidified barium chloride is added to the solution that contains sulfate ions, a white precipitate of barium sulfate should be formed, which is not a surprise to us, because we saw that when we looked at the group 2 metal ions. Now the question to ask is, why do we acidify with hydrochloric acid and say not sulfuric acid? Well, if you think about it, sulfuric acid is a source of sulfate ion, so adding that to your barium chloride would immediately form a white precipitate. So let's make a note of that. Okay, so the best way to acidify your barium chloride is to add hydrochloric acid, which of course would have H+ ions and Cl- ions, and we know that your barium isn't going to be forming a precipitate with your chloride ions. As you can see, you've got barium chloride solution, which is completely soluble. Okay, so the presence of your HCl will get rid of any carbonate ions in your test solution which might otherwise interfere with the results of your test. And over on the right hand side of the page, you should be able to see the result of the test for sulfate ions from the addition of barium chloride, and the barium and your sulfate ions pair up, as you see, to give you the precipitate barium sulfate. So we can repeat that ionic equation. So barium ions from your barium chloride, aqueous barium ions, reacting with any sulfate ions present to give you solid barium sulfate. Okay, so that's a good test for the presence of sulfate ions. Now, it is worth mentioning that you could, as we've just been discussing, the addition of hydrochloric acid to our barium chloride so that we can get rid of any carbonate ions. We could also discuss the test for carbonate ions. If we write that properly, CO3, 2 minus, and that would require the addition of so if you've got a solution that you suspect to contain carbonate ions, so for instance sodium carbonate, or even hydrogen carbonate ions, you could add your solution of hydrochloric acid, and that should lead to the formation of carbon dioxide gas. Okay, so the fizzing observed is due to carbon dioxide being evolved as a result of your carbonate ions reacting with your hydrochloric acid. Okay, so the next group of anions that you're required to be able to identify qualitatively are the halides. Okay, so when we say the halides, we're typically referring to chloride, bromide, and iodide. Of course, you've got fluoride, and you've got you do have acetine below iodine, and tennessine even, and these are all halogens, and they do form halides. But the three common ones that you will see at A level are chloride, bromide, and iodide. And again, the tests for these halides, certainly one group of tests or one reagent you will have seen previously is using silver nitrate as a test for each of these halides. And the silver nitrate is acidified, or rather your test solution is acidified with nitric acid before your silver nitrate is added. And again, this is to remove any carbonate ions that might be present. Okay, so in this instance, you don't want to use hydrochloric acid, because then you would be introducing chloride ions into your test solution, which on addition to silver nitrate will always give a positive test. So we can't acidify with hydrochloric acid. We can't acidify with sulfate either, because you would form sulfate precipitate. So nitric acid is the acid used to get rid of any carbonate ions that might be present. Okay, so since this reaction is used as a test to identify which halide ion is present, the test solution is made acidic with nitric acid. So that's what we've just been referring to. And then silver nitrate solution is added dropwise. And what would you expect to see? Well, down at the bottom of our screens, if I bring this sort of center stage, you should be able to see 3 test tubes, each containing a precipitate. On the left-hand side, we've got a precipitate of silver chloride, so silver chloride shown there, which is a white precipitate. And then to the right of that, in the middle, is silver bromide precipitate, which is sort of creamy in color, so, or perhaps more appropriately described as being off-white, so not quite as white as silver chloride. Silver bromide is sort of off-white or cream. And for silver iodide, you've got a pale yellow solution. So it's easy to distinguish the iodide precipitate, the silver iodide precipitate, from the other two. It can be a bit more challenging to tell apart your silver chloride and your silver bromide precipitates, but I will show you how you can do that quite easily. So the role of nitric acid, again, is to remove any carbonate impurities. And we can't, perhaps worth mentioning, can't use, because it introduces chloride ions. And of course, your chloride ions would form silver chloride as a precipitate, so you don't want to do that. And also can't use so sulfate ions present would also lead to the formation of silver sulfate as a precipitate. So you've got to use nitric acid. Okay, so we've discussed or described the precipitates formed for chloride and bromide. How do we tell the chloride and bromide apart? A good way of doing so is by adding aqueous ammonia and observing what happens. If you've got silver chloride formed, it should dissolve in aqueous ammonia, whereas your silver bromide will not dissolve in aqueous ammonia. You can make your silver bromide dissolve in concentrated ammonia, however. So if you were struggling to tell apart the bromide and iodide, that would be the way forward, using concentrated ammonia. Okay, so if we state that, so and your silver bromide the silver bromide dissolves in concentrated ammonia, and silver iodide does not dissolve in either. Okay, so that's how you would, this perhaps is familiar to you from GCSE, that's how you would go about trying to identify halides in solution. Now, there is another way of identifying halides in the salt, so in the solid, and this is done by taking advantage of some characteristic products formed in the redox reaction between the halides and, so the halide salts and sulfuric acid, concentrated sulfuric acid. So we'll look at that next, and then we'll look at some practice exam questions. Now, starting with solid sodium chloride and looking at the reaction between your sodium chloride and sulfuric acid, what you'll see is that it is a fairly straightforward reaction where a strong acid is added to a salt, and the salt, as a result, is converted into a strong acid. So the metal ion and the salt, in this case your sodium ion, is going to be replaced by a hydrogen from our strong acid, which is from our sulfuric acid. And so what you end up with is HCl gas being formed. Okay, so if you've got a salt and you want to liberate the acid, then you're going to be adding to that salt a very strong acid, such as sulfuric acid. So in the case of sodium chloride reacting with your sulfuric acid, what you end up with is your HCl gas, and you also form sodium sulfate. So you do form the salt of your strong acid, sulfuric acid. Okay, so nothing redox about this particular reaction. If you used oxidation numbers to work out the oxidation states of different species, you'll find that there are no changes in oxidation state, so we don't have a redox reaction. So the sodium is +1 in this instance, it's still +1 in our sodium hydrogen sulfate. You could work out the oxidation state of our sulfur, and you would find that it is +6 in the sulfate ion. It remains +6 in the hydrogen sulfate ion, so nothing changed about sulfur. Chloride is Cl-, so 1-, and it's still 1- in hydrogen chloride gas. So there are no changes in redox oxidation numbers at all. Now, when you carry out a similar reaction with sodium bromide and hydrogen and sulfuric acid, something rather interesting happens. As well as having an analog of the reaction we've just described with sodium chloride, so in other words, forming HBr gas and sodium hydrogen sulfate by reacting with solid sodium bromide with your sulfuric acid, a second reaction occurs. Now, this second reaction is a redox reaction, and we'll see why it is in a second. But this second reaction allows us to identify and distinguish the sodium bromide salt from the sodium chloride salt. Now, incidentally, before we talk some more about sodium bromide reaction with sulfuric acid, we should point out the observations made here. And in this instance, your hydrogen chloride gas would be observed as a fuming white gas, or white fumes. Of hydrogen chloride gas are produced. Okay. Now, you will get the same observation with your hydrogen bromide gas. Again, you would form white fumes, but something else is observed, and that is the fact that you will also form a brown gas, which is your bromine gas being formed as a result of the redox reaction. So you've got bromide ions, in this instance, losing electrons, so being oxidized to give you bromine. And importantly, because you've got a redox reaction, you've got your sulfate ions from your sulfuric acid, which would be the oxidizing agent, sulfate ions themselves being reduced to sulfur dioxide. So you can work out that it has been reduced by looking at the oxidation state of sulfur, which is +6 in your sulfuric acid, but is now +4 in your sulfur dioxide. So it's gained electrons. The sulfur has gained electrons. In other words, it's been reduced, and it's been reduced down to sulfur dioxide. So in red, we have a redox reaction. This is a redox reaction. And you can work out the oxidation state. So bromide, you've got -1. And over here, you've got 0. And for your sulfur, you've got +6. And +4 in this instance. Okay, so we've got redox chemistry occurring, and for as far as the observations go, your bromine is of course a brown gas being produced. Bromine under normal circumstances is a liquid, but because this reaction is exothermic and bromine has a very low boiling point, so in the 30s, you would see brown fumes being evolved. And you also form colorless gas in SO2, which is toxic. Okay, so that would be the other product formed, toxic colorless gas. Okay, so there are two reactions going on when your sodium bromide reacts with sulfuric acid. The first, of course, is the formation of hydrogen bromide gas and sodium hydrogen sulfate. That is not a redox reaction. It produces white fumes of HBr gas and sodium hydrogen sulfate. But the second reaction between the HBr that you form initially and sulfuric acid is a redox reaction. Okay, so you would form some bromine gas, you would form some sulfur dioxide gas and water as well. Okay, now let's look at the reaction between sodium iodide and sulfuric acid. And again, you've got the same sort of reaction where the hydrogen iodide gas is liberated from the salt. and you also form sodium hydrogen sulfate. Of course, the hydrogen iodide gas so is observed as white fumes. But there are other reactions going on. There are redox reactions going on, and quite a few of these. And this speaks to the reducing power of your iodide. It's a much better reducing agent than bromide, and bromide is also a better reducing agent than the chloride ion. So there's a lot more going on with the iodide. And the first reaction to point out is, of course, the formation of iodine, just as we saw the formation of bromine and SO2 and water. So this first redox reaction is exactly analogous to the redox reaction seen with our HBr and sulfuric acid. Okay, so that's what hydrogen iodide forms, or one of the things it does form is iodine. And of course, it can also, because it's so much better at reducing your sulfuric acid and your sulfate ions, it will also form sulfur as a product. So another reaction and another reduction product of our sulfuric acid is sulfur. And there is an even there is a the sulfate ions can be reduced even further, all the way to your hydrogen sulfide, which is a toxic and very foul-smelling gas, smells of rotten eggs, which you may well have come across before. So there are a number of redox reactions going on here. So iodine is observed, and it might be observed as a black solid. We annotate that. Let's perhaps use a highlighter. So it can form as a solid. And you would also form, as we've just discussed, some sulfur, which would be a yellow solid. And hydrogen sulfide gas, which would be, did not mean to erase that, there we go. So your hydrogen sulfide gas, which would be sort of smells of rotten eggs. Very toxic gas. Okay, so you can use all these observations to tell apart different halide salts. So sodium chloride, it's fairly straightforward. Hydrogen chloride gas is all that's made, along with your sodium hydrogen sulfate. For sodium bromide, as well as hydrogen bromide gas, you should expect to form sulfur dioxide and bromine gas, which can very easily be identified because of its brown color. And then for sodium iodide, you would also expect to make solid sodium along with your iodine. You would also be expecting to make some hydrogen sulfide gas, which is a very distinctive smell of rotten eggs and is very toxic. Okay, so these are all the different tests that you would be required to be able to carry out in order to identify different anionic and cationic species. And of course, as with all of these tests, it's a case of ensuring that you commit these to memory, so the reagents and the observations, as well as the quantities used in carrying out tests. And as you can see, very small quantities required to produce the appropriate results. What's left for us to do now is to tackle some practice exam questions. At this stage, I will pause to have a very quick check and see if there are any questions for me, which there aren't. So we will look at a few practice exam questions before we bring today's proceedings to an end. Okay, so I've chosen a selection of questions from a number of AS papers, the 2016 and 2018 papers to be exact. And the first one looks at the addition of sulfuric acid to two solutions of sodium carbonate and aqueous silver nitrate, and we're being asked to say what we would expect. Okay, so a student adds aqueous sodium carbonate to one test tube and aqueous silver nitrate to a second. So these are the two test tubes. And then to each of these, the student adds dilute sulfuric acid. So the addition of acid to the carbonate should immediately produce effervescence, because you've got carbon dioxide being released as a product of the reaction between the acid and the carbonate. Okay, so we can immediately rule out the first two because there is no effervescence there, whereas at C and D, you've got effervescence. So the question then is, what happens when you add your sulfuric acid to a solution containing silver ions? Okay, so we would expect to see silver sulfate being formed as a precipitate, so that leaves us with D as our final answer and D as the correct answer. Okay, so that's the first question out of the way, relying on our understanding of and recall of the observations when silver nitrate is used as a reagent, and also looking at the reaction of acids with carbonates. So moving on to the second question, which is taken from part of question 23, which is a fairly long question, but part C deals with some qualitative tests for the halide ions. The precipitation reactions can be used to distinguish between halide ions, state the reagent needed for these precipitation reactions, and of course we've just been discussing the use of silver nitrate as a reagent, so aqueous silver nitrate. And of course, aqueous silver nitrate. And if we then acidify our chloride, bromide, or iodide solutions with nitric acid, we can add silver nitrate dropwise to each of those solutions, and we would get different colored precipitates, starting with a white precipitate for chloride, and you get a green precipitate for your bromide, and a yellow precipitate for your iodide. And if you want further detail, although this question doesn't, there's only one mark, this would dissolve in aqueous ammonia. This would dissolve in concentrated ammonia. And your silver iodide, of course, does not dissolve. Okay, so this is extra detail, not required to get the mark. Okay, so just the colors of the precipitates. Here's another question which is only indirectly linked to what we've been looking at, and specifically the tests for the halides in their solid form, so the halide salts, and essentially going back the other way, looking at oxidizing the product of the reduction of sulfuric acid back to a higher oxidation state. Okay, so it says which reaction shows oxidation of sulfur, and in answering this question, you would be using oxidation numbers, right? So you would look at the sulfur in each species and see if it's so oxidation being the loss of electrons, see if it's lost electrons so that it's become more positive, it's acquired a more positive oxidation number. Okay, so if we start from the very top and deal with that, so that is in a +6 oxidation state, and it goes down to the +4 oxidation state. So it hasn't been oxidized. It's gained electrons. So it's gone from +6 to +4. It's actually being reduced, which is what we talked about when we looked at the reaction of sodium bromide and sulfuric acid. So the answer can't be A. If we look at B, we've got sulfur in the +4 oxidation state. And if we look at SO3 2-, which is the iron here, your sulfur is still in the +4 oxidation state there. Okay, so again, no change here. There's no redox reaction to speak of. All you've got is an acidic gas reacting with an alkaline solution to form salt and water. So that's just a neutralization reaction, really. And then you've got hydrogen iodide reacting with sulfuric acid to form hydrogen sulfide. As we saw previously, this is just your hydrogen iodide reducing your sulfate ions and your sulfur. So we've got the opposite of oxidation. So that rules out C as well, which brings us to the very last option. So we've ruled out the first three. It has to be this. But let's look at why it is. So you've got your hydrogen sulfide, this time reacting with chlorine. Now, chlorine is a good oxidizing agent. So given that the chloride is a very poor reducing agent, the chlorine has to be a good oxidizing agent. So you've got chlorine oxidizing your sulfur to give us HCl, and so oxidizing the sulfur and hydrogen sulfide to give us the elemental sulfur seen there. So if we work out the oxidation numbers, you've got -2 here, and you've got 0 there. So that has lost electrons to acquire an oxidation state of 0. Okay, so the answer, of course, is D. And we've got one final question to do before we say goodbye. Now, in this experiment, the student adds a few drops of aqueous sodium chloride to the reaction mixture. So the reaction mixture may or may not contain aqueous silver nitrate. So if we see the question in its entirety, we will see that there is silver nitrate being formed, which then has to be reacted away. So explain how the results would show whether all the aqueous silver nitrate has reacted. Include an equation with state symbols in your answer. So if all the silver nitrate has reacted, if you add sodium chloride, there will be no silver precipitate formed. There will be no silver chloride precipitate formed. So white precipitate of AgCl will form if silver nitrate present. Okay, so explain how the results would show whether all the aqueous silver nitrate has reacted. Include an equation with state symbols. So what we're looking at is the formation of silver chloride from AgNO3 aqueous reacting with our sodium chloride, chloride ions, NaCl. So that is aqueous NaCl, and that would lead to the formation of silver chloride, which is solid, and sodium nitrate, which is aqueous. Okay, and if we check that that is all balanced, it is indeed. Those would be your 2 marks. So I hope you have found this session useful. Certainly, if you do think of any questions about qualitative analysis that you wish for us to address, do drop us a line at boostrevision.com, and we will be more than happy to get back to you swiftly with an answer. It's been a pleasure, as always, to have you join me this Sunday. Thank you very much, and I will see you soon. Take care.